Welcome to my talk on how much SYCL does a compiler need, experiences from the implementation of SYCL as a library for NVC++. My name is Axel Alpay, I work for Heidelberg University. Currently, the situation is that multiple SYCL implementations support CUDA through Clang. This is the case, for example, for the CUDA backend in DPC++ or in HipSYCL. A consequence of this is that there's no direct NVIDIA support. So new NVIDIA hardware might not be immediately supported because it might take some time, for example, for upstream Clang LLVM to support newer CUDA releases. Also, a simple CUDA installation is not sufficient to deploy SYCL. Users would also need to deploy Clang LLVM, which might be cumbersome. And of course, NVIDIA will also not be helping with problems. As such, I think it's natural to ask the question whether there's a way to actually implement SYCL as a pure library for official NVIDIA compilers. And as it turns out, the answer to this question is yes, and we have actually done it with HipSYCL and NVC++. All of what I'm going to show you is available in upstream HipSYCL, starting from the 0.9.2 release. So HipSYCL is a multi-backend SYCL implementation that has a focus on aggregating multiple toolchains. It supports CUDA GPUs, AMD GPUs, any CPU through OpenMP, and there's also an experimental level 0 backend for Intel GPUs. It targets those devices through multiple toolchains such as OpenMP, the Clang CUDA toolchain, the Clang HIP toolchain, the Clang SYCL toolchain, and now also through NVC++. HipSYCL supports many SYCL features and is an open source project that's also used in production by larger projects. Currently, HipSYCL supports two compilation flows. One is the pure OpenMP C++ library flow, where input SYCL code is ingested by any OpenMP C++ compiler, which then produces an output binary for the host. This can be used to run on any CPU. Alternatively, there's a Clang-based flow, and this is the one that's currently used to target CUDA devices. In the Clang-based flow, the Clang CUDA toolchain is used to generate PTX. However, since the Clang CUDA toolchain cannot understand SYCL code, we add a Clang plugin into the compilation process. And this Clang plugin is responsible for detecting SYCL kernels. It then walks the syntax tree in the compiler and inserts the required CUDA attributes wherever necessary. For example, the CUDA global kernel attributes, the device attribute, and so on. The Clang CUDA toolchain then handles the rest. Consequently, with this approach, SYCL code is effectively compiled as CUDA C++ code, but we have made it so that the CUDA attributes are optional. And CUDA C++ code can then also be used within kernels. And this property is extensively used inside the HipSYCL headers, where, for example, we implement SYCL built-ins by calling CUDA built-ins. NVC++ is an NVIDIA production compiler that's part of the NVIDIA HPC SDK, and it's advertised as compiler for OpenMP, OpenACC, as well as parallel STL offloading. NVC++ also supports CUDA C++, mainly in order to be able to leverage existing CUDA C++ algorithm libraries like CUP. This support is, however, not widely known and not widely advertised. An interesting property of NVC++ is that all these models can be mixed. So, for example, you can call an OpenMP based part of your code from a CUDA-based part of your code. And as such, CUDA attributes need to be optional. Because otherwise, how would you be able to call a OpenMP-based part of your kernel where device attributes, for example, are not necessary from a CUDA-based function? For example, if you have a CUDA kernel, let's call it parallel 4 with a CUDA global attribute, and you invoke that kernel and give it some lambda function, and inside this lambda function you then call another function h. This function will implicitly be a device function and implicitly have the device attribute because it's called by a kernel. This example, of course, already looks quite a lot like what you would want in SYCL. So with this functionality, NVC++ already supports the most important feature of HipSYCL's Clang plugin. And one important thing to note is also that we really need CUDA support. We need NVC++ CUDA support over, for example, NVC++ capability to offload parallel STL algorithms, because we need to implement lower level features in SYCL such as barriers or ND-range parallel 4, local memory, and so on, which is not possible with higher level models such as parallel STL offloading. HipSYCL's CUDA support builds on three components mainly. The SYCL runtime, which in the CUDA backend is invoking CUDA runtime functions. SYCL kernel headers that are written in CUDA C++ that, for example, map SYCL atomics to CUDA atomics and so on. And then there's the Clang plugin. And as I've said, the core functionality of this Clang plugin already comes for free with NVC++. So if we take all this information together, we should be able with NVC++ to have HipSYCL's CUDA backend operate as a library for NVC++. But is this actually legal? Can we do this in SYCL? Does the specification allow it? So to answer this question, we need to have a look at the implementation options that the SYCL specification allows. And there are three implementation options that the SYCL specification defines. The first one, and the most widely used one, is the SMCP model, which stands for Single Source Multiple Compiler Passes. In SMCP, the SYCL code is compiled by one or multiple device compilers, which then each generate a device binary. For example, you might have one device compilation pass for NVIDIA, which generates PTX, one for AMD, which generates AMD GCN code, and so on. And lastly, you also have a host compilation pass, which then does the regular host compilation. In the end, everything is put together into one host binary that you can execute. Then there's another method, which is called Single Source Single Compiler Pass, or SSCP. And the main difference here is that instead of having separate compilation passes for each target, you only have a single compilation pass. So you have a SYCL code, which gets fed into a unified compiler pass. And the unified compiler then generates some sort of intermediate representation. And only at this stage is the device code, the code that's required for kernel, separated from the host code and then lowered to whatever the target device needs, to some device binary. And all of this is again put together into a host binary. Lastly, the SYCL specification also defines the library-only implementation, and it says it's also possible to implement SYCL purely as a library using an off-the-shelf host compiler with no special support for SYCL. In such an implementation, each kernel may run on the host system. So you have a SYCL code, then you have a third-party compiler, and you get some binary out of it. And this is basically what we are doing with our OpenMP compilation flow for the host system. So now it's important to realize that NVC++ follows an SSCP approach. So NVC++ has a single compilation pass for both host and device. If we now implement SYCL as a library for NVC++, then we technically have a SYCL implementation that uses a third-party SSCP compiler and therefore also has library-only characteristics. The SYCL specification says that library-only implementations are mainly intended to target the host, but in practice it turns out that there's very little difference to also targeting a device. There are very few additional implications. So we can conclude that SYCL as a library for NVC++ is likely legal, but it sort of bends the specification slightly because the specification does not really know about device library-only implementations. So what are consequences of such an SSCP design? So one is, of course, that in theory you can have better compilation times because you only need to pass the code once instead of multiple times. A consequence of you only passing the code once, however, is that you cannot use macros to specialize code between host and device passes. And there's a common pattern in SYCL code where you use the SYCL device only macro to decide if you're in the device compilation pass or the host compilation pass, and then you can optimize your code for device case or for the host case. However, the specification only guarantees that this works in the SMCP model. It does not work in SSCP at all. So what can you do instead in SSCP? So NVC++ has the if target mechanism, where you can use if target like an if statement, and then you can specialize your code accordingly using if target NV target is device or if target NV target is host. This, however, only works in control flow like a regular if statement. You cannot use this in any kind of const expression context, for example. So you cannot use it to detect whether you're in host and device pass, and then use this information to instantiate some template, for example. So how does it actually work? So the first thing we need to worry about is how kernel launches works. So what we would need to do is we need to implement the kernel launch using the CUDA kernel launch syntax with the triple brackets. This is actually fairly easy in HipSYCL, because in HipSYCL the SYCL headers, when they are compiled, they construct a function object that we call a kernel launcher. And the kernel launcher is then passed to the runtime and invoked whenever the runtime wants to invoke a kernel. And the kernel launcher, since it's compiled as part of the headers by the SYCL compiler, it can contain arbitrary CUDA code if you compile it with NVC++. So that's easy, that's solved. Now we also need a generalization for SYCL device only that also works in SSCP, because SYCL device only and other macros are also massively used in the HipSYCL headers to select appropriate backend implementations, for example, for our built-ins. And you can see an example here. So imagine that we want to implement the SYCL sign function. Then we would need to, maybe depending on the backend, map that to different actual built-ins. And what we have done is we have introduced the HipSYCL if target mechanism, which generalizes to both the SMCP and SSCP case. And we can then just say, okay, if we're targeting host, then we're calling std sign. If we're targeting CUDA, then we're calling some CUDA built-in, and so on. And so what we've done is we had to refactor all the headers to rely exclusively on this HipSYCL if target mechanism. And another thing that also turned up is that we also cannot do some data layout optimizations anymore based on host or device, because we cannot, we can only detect whether we're in host or device with this if target mechanism inside the control flow. So we cannot change how classes look like, for example. And this affects something that we call on-demand iteration space info. And this is an optimization that affects SYCL classes like group or item. And normally these classes need to store the global ID, local ID, range, global range, local range, and so on. But what you can actually do if you're compiling for something like CUDA, you don't actually need to store that information. You can query it on demand from backend built-ins such as CUDA thread index, because those are very efficient and they have this information readily available. And this storage optimization is, however, not possible in NVC++ because we also want to support the CPU backend. And since we cannot have different data layouts between CPU and device compilation paths, because there's only one compilation path, we cannot do this. But this is really the only case of code divergence in kernels between HipSYCL's Clang-based CUDA backend and the NVC++ CUDA backend. Otherwise, exactly the same thing happens. So last thing that we then need to do is we need to add support for this new compilation flow driver inside our SYCLcc compiler driver. And you can use it by just passing CUDA NVCXX to the HipSYCL target specification. One thing that we're also working on that's not yet supported is to also add support for additional Clang-based compilation passes for other non-NVIDIA targets when you're using NVC++, but that's a work in progress. So what are some of the limitations of this approach? One limitation is, of course, that since this approach has library-only characteristics, everything that affects library-only implementations also affects this. And while library-only implementations are explicitly allowed by the specification, it turns out that some features are not well implementable. So that's, you can call it a bug or a contradiction in the specification. This affects, for example, attributes. So the SYCL specification has attributes like required workgroup size, and if you cannot control the compiler because it's a third-party compiler, then obviously you cannot add in any custom attributes. And then there are also some APIs like kernel bundle where you would need to have control over how kernels are compiled or jitted, or you need to expose some sort of introspection into kernel properties like how much resources it requires, and these kinds of things might also be limited in a library-only implementation. But this is the case for any library-only implementation, also for the existing host library-only implementations. That's not a new problem. In addition to those issues, there's one additional thing that popped up that we noticed, and this is SYCL one-to-one hierarchical parallelism. This is a programming model where you first say what you want to parallelize over your workgroups, and then you can specify code that's executed once per workgroup. And then inside the scope, you can again fan out and then say what you want to have executed in parallel for each work item within that workgroup. And if you want to implement this on GPUs, you need to have dedicated compiler support because you need to make sure, for example, that code that's here is only executed once per workgroup. So you need to mask out all the other work items. Since we cannot add in any additional compiler logic into NVC++, this cannot be supported with NVC++. This is not a huge problem, however, because this model is discouraged in SYCL 2020 anyway, so people shouldn't use it anyway. And as a potential successor, we have proposed the scope parallelism model. That's available as an extension in HipSYCL, and this extension is also implementable with NVC++. We also noticed multiple compiler bugs with NVC++. And we found those as mainly as crashes when working with the HipSYCL unit tests. And we are reporting those bugs as soon as we find and isolate them, and we report them to NVIDIA. And the good news is some of those are already fixed. So yes, you actually really get NVIDIA support for using NVC++ with HipSYCL. And those issues most relate to complex patterns that are used inside our unit tests, like massively nested lambdas in the scope parallelism extension. And I've so far not yet seen any issue in real world code with NVC++. So in practice, it tends to work very well. Now let's look at performance. There's an interesting angle here, because when people compare SYCL and CUDA, people usually compare Clang-based SYCL implementations with NVCC. And if you do this, then you're changing multiple variables. You're changing the compiler front end, you're changing the code generation backend, you're switching to a different programming model. With the NVC++ library-only backend in HipSYCL, we can, however, separate these effects. We can look at NVC++ compiling both SYCL and CUDA code. So basically we can have the same compiler and only switch the model. And then we can make a statement about what the impact of the SYCL C++ abstractions is. Or we can look at HipSYCL using Clang CUDA versus HipSYCL using NVC++. So we can keep the model the same and we can keep the code the same, but we are using a different compiler. And then we can make a statement about what the impact of using open source compilers is versus vendor compilers. And in the results that I'm going to show you, I've used a GeForce GTX 1080 Ti. The benchmarks are from the Hackbench benchmark suite, which is a collection of benchmarks aggregated from multiple sources, and also Babelstream. And this is HipSYCL 0.9.2, CUDA 11.6, Clang 13, and NVC++ 22.1. So what you see here is the performance, the relative performance of HipSYCL using NVC++ normalized by CUDA using NVC++. And what you can see is that for certain benchmarks like MD5 hash, there's not really a difference. And also Babel stream tends to perform fairly well. I've here looked at Babel stream with default problem size and Babel stream with quadruple problem size. You can see that with quadruple problem size, it performs better. So SYCL performs better compared to CUDA. And this is because certain runtime overheads or kernel launch issues are then not as noticeable. And I've also looked at FFT, which does not perform so well. And this seems to be mostly the case because it submits fairly short-running kernels. And then you can notice a runtime overhead, especially because these kernels also use buffers, and buffers always need a bit more work for the runtime compared to pointers, as it happens on the CUDA side of things. Because with buffers you need to do the dependency analysis and construct a task graph and so on. And this is SYCL, a HipSYCL using NVC++ normalized by HipSYCL using Clang. And what we see here is that Clang actually performs very, very, very well. So there are only 2 benchmarks where NVC++ performs noticeably better than Clang. And there are several benchmarks where Clang actually is faster than NVC++. And so clearly performance is not a reason to prefer vendor compilers. Open source compilers deliver great performance. However, day 1 hardware support or ease of deployment might be a reason to consider vendor compilers. So conclusions. So what I've shown you are results from, as to my knowledge, the first library-only device backend in a major SYCL implementation. And this allows you to use a vendor-supported compiler, namely NVC++ for NVIDIA hardware. And this can, for example, simplify the deployment of SYCL if the NVIDIA HPC SDK is already pre-installed, because you do not need LLVM. You can just grab HipSYCL, point it to NVC++, and you're good to go. This backend uses the exact same code paths as HipSYCL's Clang-based CUDA backend, except that there's no support for hierarchical parallelism, and that certain optimizations are not available, but those have a very small impact. In general, be aware that SYCL implementations might rely on SSCP. Be very careful with the SYCL device-only macro. Unfortunately, the SYCL specification does not really have a standardized alternative for SSCP. The SYCL working group should try to resolve the library-only issues. And my personal opinion is that there's also no reason to limit library-only backends in the specification to the host. The spec should be clarified to also allow device library-only implementations. So what does this all mean for SYCL in a wider angle? So clearly we have shown that SYCL can actually be implemented for devices as a library for third-party vendor-supported compilers. So this means that SYCL may not have to be a full-blown compiler toolchain. It could also just be a portability layer for third-party compilers, similarly to, for example, Cocos. This works as soon as there are programming models available with automatic kernel outlining, where you don't need to explicitly mark each function that should be compiled for device, as you'd have to do with the CUDA device attribute. For such a use case, SYCL should focus on library-only friendly programming models, such as HipSYCL scope parallelism over ND-range parallel 4, which is known to be difficult to implement on CPU in a library-only implementation, or SYCL 1-to-1 hierarchical parallelism, which is difficult on a GPU to implement in a library-only implementation. So I want to leave you with the question, what does SYCL want to be? Thank you.